Hello, community. So great that you are back. I was asked by quite a lot of my viewers to explain reinforcement learning. Can I give an overview? And I thought, hey, that's a great idea. Plus, I will show you the next AI development if we look here at reinforcement learning system in the future. And I will show you how we know today already what will come in the very next future. Because there is a real close connection between theoretical physics here and especially reinforcement learning in our AI. So I will give you a very personal introduction. These are just my thoughts. I could be completely wrong, so please, you have to help me. You have to think alongside, but I want to share my thoughts with you, and I want to give you an introduction from my point of view. You know, artificial intelligence, great, everything today is reinforcement learning. And there's a beautiful mathematical connection to physics and especially here to the mathematical construct that we built here in statistical mechanics. Now, the idea is simple. If we know everything on the connects to reinforcement learning, we already have the knowledge of physics in quantum mechanics. So the way is simple, not to go and develop AI further with just more of the same, more NVIDIA of the same GPU cards. But the idea that I want to present to you is, hey, if we understand the physics of AI and we understand where the AI physics is currently, and it is statistical mechanics, and we have the complete theoretical physics and mathematical apparatus to formulate quantum mechanics, and we can now map quantum mechanics to quantum AI and quantum reinforcement learning, why not have a look at the future? Talking about to have a look, you know, it is all a question of a perspective. Now think about Rubik's Cube. If we have solved it, it's so simple, no? We have a dimension I call AI. AI understanding, AI theory, AI application. But we also have another solved phase of Rubik's Cube that's called mathematics. Because everything, the ideas that we have to encode in mathematics. But the ideas that we have in coding AI are very closely related to our understanding in physics. Because, yeah, it's the rule, the law of nature. So physics describes nature. And AI is part of our nature, if you want. So everything that we have in physics discovered in the last, I don't know how many thousand years, is also part of our knowledge. If we have this constellation or this representation of a Rubik Cube, it's easy. But you know what we have? We have this representation of a Rubik Cube if we are in the real world. So just let's say blue here are the AI theory from reinforcement learning. Green is the physics that we understand. This is the background to AI. Pink are the pure mathematical, formal, if you want, code implementations. And yellow is the code itself. So this is now an interesting structure. So let's explore this. Now, talking about reinforcement learning, what are the foundation? Just very short, 1 minute. Subfield of machine learning focuses on training agents to make sequential decisions by interacting with an environment. We have the basic idea of a Markov decision process where we have some tuples defined. This is a set of states representing possible configuration of the environment, then a set of action our AI system can do available to the AI agent. Then we work with transition probability function to describe how an action that the AI takes leads now from a state S to another state S dash. We have a distribution of the initial state. We have a reward or the immediate reward obtained after execution and action A in a particular state S of the agent. And we have gamma. Gamma is the famous discount factor that balances immediate and future expected rewards or calculated rewards. And the goal of reinforcement learning is to find here an optimal policy pi given a specific state S of the system and an action A taken, which maximizes now the agent long-term reward. And you know the whole RL is just a mathematical optimization theorem. So formally, if we work now with the classical one, we have a long-term reward. This is defined here by the state value function called V pi on the policy pi. Of course, we go further on from a state action function to an action value function. This is our Q learning with a particular policy pi, and the difference is simple, our advantage function A of the policy pi, and this is defined here. So in reinforcement, what we do, we have a state value function V of pi, which represents the expected total reward for an agent starting here from a state S. But different now to this is now the action value function Q. This is the expected total reward from an agent to choose now an action A while in a particular state S. So the advantage function now measures here is our metric, the expected additional reward for choosing now a particular action A at a particular time t over the expected reward of the policy. And the expected total reward of a policy pi is then here defined in this simple equation. So by maximizing now the expected total reward, an optimal policy, and we denote this here by pi star, can be derived, can be found. This is the solution of our optimization problem, enabling now our AI agent to receive the maximum reward in the environment, and the agent learns something. Great, this is reinforcement learning. This is our actual state. If you want to read more about this, I recommend this paper by Northwestern University. So what we see now that reinforcement learning and statistics, they share a lot of things. But you know what? Why not go a step further? Why not go here with Rubik's Cube here with our different perspectives, and we combine this now with Schrödinger's cat? You know, this famous cat, is it alive or not? What would happen if we have a Gedankenexperiment and we combine those, no? And I ask here Google to show us here some quantum verification. What would be the next step that we take? Or if you want to hear it even more heavier, if we have here kind of a quantum field theoretical approach now for the very next AI systems, it is not easy. So let's start now with our basic understanding of reinforcement learning. And yes, I know some of you are very far advanced experts, but hey, I wanted everybody who sees this video, so I start here with a basic introduction to bring you up to speed so we have everything, we know everything together. So the core idea of reinforcement learning, agent interacts with the environment to learn a policy, and a policy is nothing else than a way of choosing specific actions to maximize here the cumulative rewards over time. It's an optimization problem. And we have a particular states, we have an action, we have a reward function coming back as a feedback, and we transition to a new state as dash. Now, you know, we have three main methodologies. We have the typical Q learning, where we learn here a Q value function here, dependent here on the state of the system, given here a particular action, and this is simply the expected cumulative reward for taking action A and following the best policy thereafter, and our key equation is a simple equation. Then we have a policy gradient methodology. You just think about backpropagation. You say, yeah, and of course. The idea is instead of learning now our Q values, we directly parameterize the policy pi theta for a particular state and a particular action and optimize this via a gradient descent to maximize the expected reward. So you see, also an optimization, but now with a different methodology, with a different mathematical notation. And then the third one here, or the fourth one, we combine those. We have now the best of both worlds. And this is what we know, the actor critique method. So we combine the value-based and the policy-based methods. So the actor updates now the policy p theta, and the critique estimates now the value function that we have, either V or Q here, the action state function to guide here the actor. So the critique learns the value function, and the actor using here the critique feedback to update the policy via the gradient descent. And the policy gradient here with a critique or an advanced actor critique has a simple mathematical expression where we have also defined the advantage. So this is here very simple, our intro. And if you want to see here this compared here, Q learning, policy gradient, and actor critique, you see what is learned. Here we have the Q values and the policy, and actor critique, best of both worlds. Great. So, end of introduction. Let's start. Now, you remember in reinforcement learning, we weight our trajectories by a particular factor, and this is the exponential factor of a reward divided by a but very particular temperature, an exploration temperature. Now, you know, in statistical physics, we weight here our macrostate also by an exponential function here of an energy divided by the real temperature. Now, guess what? What if these coincidences here are not coincidences, but just, if you want, a tip of an iceberg showing there's a deeper duality and there's a deeper connection between AI and what we know about physics? It is rather easy. Just think about a robot navigating here a maze. It's possible. Path is like a microstate, if you want, in a physical system. And the robot now exploring the maze has a lot of possible paths, so we have a lot of microstates. And by adjusting how we sample now the path, we have here the temperature as a free parameter, we can control, you know what we have, always this delicate equilibrium in reinforcement learning of exploration versus exploitation. And you know what? This is now almost identical when a physicist cools down a material to induce a phase change to the real physical system. So we can use now the very language of physics, the mathematical notation, to help us understand and even design smarter large language models. Let's start with this. What is the main idea in my simple world? So we use here both in physics and in reinforcement learning, we are looking for the best probability distribution that balances here the optimality, the optimization problem itself, against a randomness. And this is important. We just do not want the perfect system that is then determined, because if you think about quantum mechanics and Schrödinger's cat, we need this randomness here for very particular reasons. So, you know, if you just go to classical mechanics, statistical mechanics, Gibbs distribution. Here we have a probability of the system being here in a particular state. And if you have here this expression, you are familiar with this, we have here a partition function that is normalizing here our complete distribution and simply assigns probability to our microstates, to our robot in the maze if you want, so that lower energy states are more likely, are more favored, yet we do have thermal fluctuations that remain possible. We have here an entropy term. Now, if you say, wait a minute, yeah, of course, it is also the Boltzmann distribution. If you like this, it's a probability distribution or probability measures that gives the probability that a system will be in a certain state as a function of the state's energy and the temperature of the system. Great, and here we have our exponent, our function that we know. Great, yeah, Boltzmann constant K, we will set Boltzmann constant for our ideas equal 1, but let's start. And then we have in AI reinforcement learning. And you know the Softmax function. The Softmax function assigns probability to actions A in a state S so that the higher reward actions are more likely, yet there's still a little bit of a wiggle room that we have also exploration. So what is our probability here of taking here an action A in a state S? And look at the mathematical formulas. If you say here Boltzmann constant equal 1, you might say, this looks interesting, no? Because the algebraic backbone is identical. Is this a coincidence? Yeah, for my younger viewers here, the Softmax transformation is simple. It transforms here particular action values into a probability distributions. So it enables, if you want, a probabilistic action selection. Therefore, we have our beautiful equilibrium. We have a temperature parameter now called tau, never mind. This controls how greedy now the selection is for the deterministic version, and we use it in a policy definition. So, in reinforcement learning, the agent now must choose action based on their estimated Q values. So those are nothing else than the expected future rewards that we can calculate. So rather than always choosing here the best available action, the highest Q value, what we call greedy, Softmax has some very particular functionality that we designed in a way that Softmax allows now for exploration by choosing here less optimal actions, sometimes with a probability depending here on their Q values. So if you want a formula, I hope you're familiar with this, for a vector of action values from Q1 to Qn, the softmax probability of choosing here a particular action I, where I is element of n, is this probability here. And you might say, what a coincidence that this is a probability that we already know here from Boltzmann equation. So in reinforcement learning, we use here the softmax policy to balance choosing here the high reward action with still exploring others. So our Q function is now the expected reward of a particular action A in a particular state S, and the temperature controls how much randomness we allow here. Large temperature makes all actions almost equally likely. Small temperature makes you always pick the highest Q actions. Now, this principal temperature control here is exactly now in the real physical world like cooling or heating a physical system. Too hot and you wander randomly, you have a gas, or too cold and you freeze into a block of ice, and this is maybe a suboptimal choice if you think about the gradient learning on hyperplanes. So you see, what a coincidence, and I picked this formula on purpose because I think it's an elegant way to introduce you here to this, if you want, analogon between the statistical mechanics, the Gibbs distribution does exactly the same thing for the microstate with a particular energy hyperplane, and the reinforcement learning where we have the softmax policy for our Q function. Now it turns out it is not a coincidence. Because if you think about, we see similarities that we can substitute. Yeah? Our Q function, our action in a particular state, and the negative energy in the Boltzmann distribution, our policy pi, and our probability distribution, temperature, T or tau, never mind. And we can, one constant with just 4 dimensional ideas, we set equal 1. But this means now, or does this mean, that the reward function, or the reward complexity in reinforcement learning, plays now the same role as a negative energy in theoretical physics, and the very particular temperature parameter T or tau governs now the trade-off between the best choice and the random exploration in both worlds. Now it turns out that the reward function in reinforcement learning that we use is not something that was invented by AI or for AI or by OpenAI. The reward is very simply, just from another perspective, if you want to take Rubik's Cube, and now we look at another representation on the next phase of Rubik's Cube, it is the negative energy in physics. So we just found the same law, if you want, or whoever coded here this particular AI code know exactly was a theoretical physicist and said, hey, I know how to solve this optimization problem in theoretical physics, so guess what? I use now the equation that I know, and I insert it now in reinforcement learning, and I call it reward instead of energy. What a coincidence. But you see, it is so closely connected. The moment we understand here the reinforcement learning ideas and methodologies and formulas, and we understand physics here, and the simplest form of physics, statistical mechanics, you can see here that there is a strong algebraic connection between the ideas and the formulas and the code that we apply. So, you understand physics, you understand AI. Both formulas use here the same exact mathematical mechanism to trade off energy or reward against entropy or randomness. And you say, that's absolutely interesting, because now in physics, so we have now this probability distribution with this equilibrium, and it turns out the Gibbs distribution or Maxwell distribution is not just an arbitrary choice, because it arises here from a fundamental thermodynamic principle in physics. And yes, it is, maybe you know this, Boltzmann distribution here is precisely the probability distribution over the microstate X of a system that minimizes the Helmholtz free energy for a system in a thermal equilibrium at a particular temperature. So, this is no coincidence. This is the result here of a minimization optimization problem. This is here precisely the probability distribution of a physical system. So now you know that we have to go the next step. You know physics, no? Just think about atoms. No? We know that general systems in nature don't always maximize the entropy. That's wrong. If they would do this, everything would just fly apart. We have uniform high disorder form of gas. But the system have a counterforce. No? Systems like atomic structures tend to minimize their internal energy. So for example, atoms bind now to form molecules, or the structure of atoms itself, because there's something beautiful. A bound state here has a lower energy and is therefore stable. You see here optimization and symmetry and, if you want, Erhaltungssätze. So, but let's look at the competition, because this is nice. Now we have two forces, if you want. Yeah? So we have a tendency to minimize the energy of a particular atom, the electron, if you calculate here the particular configuration here for a particular element. You want to achieve stability, that the element is stable. And you have a tendency to maximize the entropy to achieve disorder or spread or some dynamic, and this is especially interesting if we go then to quantum systems. So, basic physics, when a system is in contact with a heat bath at a constant temperature and a constant volume, the quantity that the system naturally seeks to minimize. This is not a real parameter that we minimize, what's called here in classical physics, in theoretical physics, Helmholtz free energy. Great. So this means at low temperature, if you have a small temperature here, the E term dominates. No? The system prioritizes minimizing the energy. Even if it means here low entropy, it forms a crystal. When it's real cold, water freezes to ice and kind of a crystalline structure. At higher temperature, so if our T becomes bigger and bigger, the minus Ts terms dominates. So the system prioritizes now here, maximizes the entropy, even if it means a higher energy. This means here you move here to a phase transition to gas. So this kind of temperature dictates here the relative importance of the energy minimization versus the entropy maximization. So we do have, think about in AI, a hyperparameter, very sensitive to this hyperparameter, especially is water ice or is water a vapor. And we have here the same algebraic situation. Now, if we add now the entropy bonus to our reinforcement learning objective, you are effectively minimizing something that is a real analogon here to the physical free energy. What a coincidence. So we are talking now about maximum entropy reinforcement learning, also called soft RL, but I stay with maximum entropy RL when you see exactly here the term. So we modify here the standard reinforcement learning objective to include here an entropy bonus. So what do we have? We have here our classical usual reward from the environment, and then here we have with H the entropy of the policy at a particular state, as in the particular time, T, plus an alpha parameter. Now, alpha again is something very specific. It is our temperature parameter, or tau, whatever you'd like to call it, that controls now the relative importance of the reward versus the entropy bonus. So you see, we use here our idea from theoretical physics to build now here a mathematical formula for the optimization problem of a maximum entropy reinforcement learning system. What a coincidence. I would love to know if the one who had this idea for reinforcement learning was or studied physics and said, hey, I know a formula who achieves exactly this. This is exactly what I learned in physics. Or it was really discovered, if you want, independently. Whatever. We have an understanding that they are connected. Shannon's entropy formula H, you are familiar with this. So, alpha. If alpha is low or 0, the agent focuses entirely on maximizing the rewards. This is our standard reinforcement learning. The optimal policy might become deterministic. Entropy is 0 or close to 0, so we have almost no uncertainty. However, if alpha is high, the agent cares a lot about acting randomly with a high entropy policy, even if it means sacrificing some of the good reward function. So the optimal policy will be much more stochastic. So you see exactly this temperature alpha or tau balances here exactly here exploitation, so getting higher reward function, higher rewards back, versus the exploration acting randomly to discover new things and maintain here stochasticity. Really interesting. If you want to learn more, there are dozens of papers. I would recommend this one about maximum entropy reinforcement learning via an energy-based normalization flow. This is from Taiwan and NVIDIA. It is already an old paper from October 2024, but I like this paper. And you know what they start here? Maximum entropy reinforcement learning. Yeah, and you have the first 17 references here. I'll show you here 14. Just giving you, explaining here what we know about maximum entropy reinforcement learning, plus the very first reference paper. It's so beautiful. It starts with path integrals and symmetry breaking, and you immediately think about theoretical physics. Now, in this paper, they give you here a beautiful step-by-step deduction, not as simple as I did. I did a very simplification because I wanted here to make clear what is happening. If you go a level deeper, here you have a beautiful, and this is why I like this paper, here you have everything you need to know. Relative importance of entropy against the reward. Here you have now the soft Q function defined here with a soft value function. And if we go further, we have then the soft value estimation in SQL. But SQL is not what using a database. It is simply soft Q learning and soft value estimation and SAC. And SAC stands for soft actor critique models. And you remember at the very beginning of the video, I explained the actor critique model to you. And now we have here a soft value estimation here, where we, as you can see now, the soft value function V can now be estimated here with this particular approximation. Great. If you're not really sure about the mathematics when you read the paper, never mind. I have a particular video I called AI Math Explained, the easy way. And whenever you see those expressions, I have here a particular video where I explain, my goodness, in 52 minutes. My goodness. Here, the basics of AI mathematics. But let's come back to our topic of today. So you see, in physics, we have here a system at a particular temperature. T seeks to minimize the Helmholtz free energy. Equivalent seeks to maximize here the negative energy. And with our maximum entropy reinforcement learning, we have an agent with a particular temperature alpha or tau seeks to maximize the entropy regulated expected reward function. And let's say, hey, this is great. Now, if you want to do this, we can go a step deeper, no? Because you recall the initial mapping that we have with our acute learning with a negative energy. So this implies that the high reward, the reward R or the Q, is kind of similar to a low energy minus E. This means when the max entropy RL per step objective is then to maximize here this expression, but this is here directly analog here to the physics, maximizing here the system entropy times the temperature minus the energy. You know this formula. And this means now that maximizing here the reward plus a temperature-dependent policy entropy in reinforcement learning is mathematically equivalent to finding here a policy that behaves as if it's minimizing the physical free energy function. How beautiful is this? What a coincidence. No, it is not a coincidence. It is just physics. AI is physics. And you can use also the perspective of physics to understand AI. Or if you are absolute in abstract mathematical worlds, use the perspective of pure mathematics to understand AI. I guess you will need both classes. Okay. So this means now, in my simplification, that everybody is with me, or you say, hey, I like this sort, or maybe you say, hey, I don't follow you, I have to go pure mathematics. Choose whatever you like. Just want to tell you, the agent, if you want, in this maximum entropy reinforcement learning behaves now like a simple physical system trying to find here a low energy, this means a high reward configuration, while, you know the balance here, the equilibrium, while also trying to maintain a certain level of thermal disorder, or in EI, we call it a policy entropy, with the trade-off governed here by the particular temperature, alpha, T, or tau, or whatever. Isn't this elegant? So we defined the behavior of an agent in a maximum entropy reinforcement learning scenario, and this agent behaves exactly like a physical system. What a coincidence. Okay, let's increase the complexity, because I know you say, hey, don't make it so simple, give us a little bit of a challenge. No, so when you add this entropy term to the objective, your classical Bellman equation, this is our classical Bellman equation, our action value function, functional or operator becomes later, changes. Standard reinforcement learning without entropy regularization, the Bellman optimality equation here is this. So the value of taking here a particular action in a particular state equals the immediately reward, or given here a particular state A, state S with an action A, plus the term here, a discounted future reward from the best next action A dash in the next state S dash. Great. So what is now the soft Bellman optimality equation if we go to the soft version for an entropy-regularized reinforcement learning? Guess what? This is it. Look how beautiful this is now. So, now time for another insight. The policy that satisfies now this objective of maximizing the reward and the entropy term turns out to be exactly the Softmax or the Gibbs or the Boltzmann policy we started with. So now, come back to the beginning of the video and I showed you now what a beautiful result. So this means that the Softmax policy in AI and reinforcement learning isn't just an ad hoc way that some people in AI discovered and say, this is now what we apply to get here an exploration. No, this Softmax policy term is the optimal policy under the entropy regularized objective. So there's nothing like a coincidence in AI. We can explain this with physical system. Yeah, if you want to see here, I have here very simple, the physics here, energy, system entropy, temperature, Helmholtz free energy, minimize here the free energy, equilibrium distribution is Boltzmann, partition function, and principle of minimum free energy. And I show you here the corresponding ideas of reinforcement learning, particular here for the soft actor critique for the SAC model with a maximum entropy reinforcement learning mechanism. And you see, instead of system entropy, we have the policy entropy. There's a temperature. It's not really the physical temperature. It is here a particular temperature of this distribution. There we have reinforcement free energy, optimal policy, Softmax, of course, partition functions, and the principle of maximum entropy for the policy. But you see all the formulas and all the ideas and all the terms, the algebraic construct is absolutely similar. So AI is nothing new. AI is just coded theoretical physics for a particular neural network. But it is physics. It is a physical system. There's nothing on new ideas or new reinforcement learning didn't exist before. Yeah, it was named a different way in physics. But it is in this new representation, if you think about the surfaces of Rubik's Cube, it is just another face representation to AI. But inside of Rubik's Cube, where all the faces come together, it is physics. Okay, next. Okay, I think next I do another video because... Okay, next. Path integral. If we want to go the next step, we have to go to path integrals. And here our AI correspondent would be trajectory. No? We have here kind of an analogy between summing over all path in quantum mechanics. Yeah, careful. The algebraic backbone, but we operate on different mathematical spaces, especially in quantum mechanics. We go here not just in real spaces, we have here complex numbers and we go here in complete different mathematical constructs. But whatever construct we choose and whatever possibility we have for a mathematical operation in these new mathematical spaces, the basic form of interaction or describing a system or optimizing a system, we always come back to the same algebraic solution. So it is not the same. Quantum mechanics and AI is not exactly the same because the mathematical spaces that we build to operate our ideas are mathematically different, have to be different. But the rules and the formulas and our insight and our understanding are almost identical. Yeah, so we have path in quantum mechanics, as I told you, a complete different system and summing over action sequences and reinforcement learning. And yes, I'm gonna show you that there's something real similar. You can see this in Hamiltonian Jacobi to Schrödinger, Erwin Schrödinger. A continuous time Bellman equation goes then into a Schrödinger-like form. And if we really then take the step with a quantum idea by promoting now the probability that we have now to probability amplitudes, and we change our policy if you want to kind of a quantum journal, this then opens really up the door to a quantum enhanced reinforcement learning methodology. So you see, I have here a complete different approach. It's just my idea that I say, you know, what is the future of AI? Since AI itself is physics, but is standard classical physics, I know that I can say, I know how physics will evolve. It will evolve to quantum mechanics, move from quantum mechanics, then the next step. And if I map this back to our AI space, I know exactly what formulas and what idea to implement. So if you want my next video, one of my next videos has AI in the next 10 years. And yeah, it is absolutely crazy to write this, but you know what? If I really go from quantum mechanics here to a quantum AI system, a quantum reinforcement learning in the classical quantum mechanical way, I also know, if I go here again on the physics trajectory, from quantum mechanics to quantum field theory. So I know how to modify my mapping from quantum mechanics to quantum AI, and the mapping from quantum field theory to quantum field theory AI applied. I hope we will achieve this in 10 years. I have no idea. This is just a personal estimation. But you see, I like to see AI not just a trial and error. If somebody buys now 1 million NVIDIA GPU of the next generation and puts here, I don't know, supercomputer, whatever it is called here, I don't know if more of the same is the way to solve the way to quantum AI. I think it is much more elegant if we have a deeper understanding of the physics and of the statistical mechanic formulas and the principles that we already discovered hundreds of years ago for mechanics. And now we go to Feynman integrals in quantum AI and we apply the knowledge that we have from physics, from quantum mechanics, and we even have an outlook, if you want, for quantum field theory. Some are already talking about a string AI idea here in very particular mathematical spaces, but yeah. But you see the idea? So the future of AI, my goodness, it will be breathtaking. It will be amazing. Not because those people who do AI currently will then have 1 or 2 million NVIDIA GPUs and no idea how to implement it, because there will be some brilliant young students all over the place, from China to the US, that will understand the way forward for AI. I hope you enjoyed this video. It was a little bit crazy. I'm absolutely aware of this, but I just wanted to share my personal thought about the development of AI and what you can expect in the future. If you kind of like these crazy videos, why not subscribe? And I will see you in the next one.